All right, this is Mr. McCord's AP Chemistry class, Unit 7, Equilibrium. We're going to be looking at some of the topics today that are wrapped up in equilibrium, including reversible reactions, how they work, how we write out the chemical equations for them, how we do some math with them to figure out the concentrations or pressures of the reactants and products involved, and all that kind of fun stuff. So first off, stuff that AP wants us to know for this. There are a lot of different things that are reversible, whether it's something you can physically observe in life or if it's something that we can describe with a chemical reaction equation. In terms of chemical reactions, we can have a lot of different types of reactions. We can have acid-base reactions, we can have redox, we can have single displacement, or we can have synthesis. It doesn't really matter. The only thing that matters is that the reaction can go the other way. Since we're coming from thermodynamics, that means that the reaction should feasibly be able to be turned around. All right, we want an activation energy barrier that's not super high, and we want a difference in energy from reactants to products. Our change in enthalpy should be pretty low. We should be able to turn the reaction around and still have it be able to move in the other direction. Typically, when we write a reaction left to right, we call that the forward direction. When we turn it around the other way, we call that the reverse direction. Okay, so we don't really have a way to specifically say, oh, this is the right way or the wrong way for a reaction to happen. It's more of just which way is easier. We tend to write reactions going in the forward direction for the way we expect it to go, but we don't have to. We can turn it around any which way. To show that the reaction is happening in both directions at the same time, simultaneously, not one then the other, then one then the other, we use a set of harpoons. It's these little arrows right here. I'm going to turn on, these are pointer. Okay, so this little set of double arrows right here, the harpoons kind of go in one right and one left, shows that this is a reversible reaction. Sometimes you'll see people use full arrows, so it's like that. I'm not a huge fan of it. I like the harpoons a lot better. I think it looks nicer. But there's not really anything technically wrong with that. Okay, so again, reactions that are reversible don't reverse. They don't go forward and then turn around and reverse and then go back forward again. They're constantly going in both directions. After all, if it's capable of doing it because the energy difference between the reactants and products is not that much different, what's stopping the products from going back to what we call the reactants? The reaction can go back the other way. Okay. Now, the equilibrium part of this happens when we have the reaction seem like it stops. It's like everything kind of settles, the dust settles. Okay. Now, in reality, the reaction is always, always, always happening. Right? It is a dynamic chemical equilibrium. But it's hard to tell if things aren't changing, even down to the chemical level, stuff that we wouldn't even usually see, but our concentrations of our chemicals are not changing, and our partial pressures of gases aren't changing. All right? Some things that AP wants us to know for that. Again, we can't observe changes even down to the nitty-gritty chemical level. We can't see concentrations and pressures changing. We have reactants and products at the same time coexisting together, and they're constantly moving back and forth at the same time. The forward direction reaction and the reverse direction reaction are going at the same time. Now, the way we get it so that the concentration of the pressure doesn't seem to change is the rate forward is the same as the rate backward. Okay, we have the kind of speed of the reaction going from left to right just the same as the speed of the reaction going from right to left. So anytime we use up some reactants to make some products replace those reactants. They go back the other way and remake them. Okay? That doesn't mean we're going to wind up with an equal number of reactants and products, okay? But the reaction hits equilibrium when we stop seeing that change. All right, now to show that an equilibrium has been reached, where we have no more changes in the concentration of the partial pressures as the reactions have kind of leveled out going forward and backward at the same time. We can show this in a couple ways, but one of the easiest ways to visualize it is with a graph. So let's look at this, how we can graph it out. Okay, on the left, we have a kind of picture of some N2O4 that is frozen. As it warms up, it moves a little bit more and more and more, and instead of just melting into a liquid and eventually boiling into a gas, that N2O4 starts to break up. It turns into two NO2 molecules. So we go from one of these N2O4s to two of these NO2s. All right. Now that doesn't just proceed only in the rightward direction. We do make a lot of NO2, but at the same time, this reaction can go back the other way. We don't end this reaction, this process, with only a bunch of NO2 in this little glass tube here. Instead, we have a mixture of N2O4 and NO2. And that reaction continues. We continue to take N2O4 and break it into two NO2s. And we also have two NO2s meet up and reform to make N2O4. We reach an equilibrium when the rate of that forward process going from the N2O4 is equal to the rate going from the the NO2 to the N2O4. So this direction is the same as this direction. On a graph of concentration versus time, concentration would be in molarity. Forgive me, I'm using a mouse for this. All right. We see the equilibrium reach when our concentrations level out. Okay, again, they're not equal to each other. These don't meet on the same line in between, but our N2O4 is being converted into our NO2, and so its concentration drops and drops and drops, and eventually it stops. And our N2O2 concentration grows and grows and grows from nothing as it's being produced, and then it stops too. All the while, the reaction's still happening. Over here, we can look at the graph of the rate. Since our equilibrium is defined by the fact that the rate of this reaction going forward is equal to the rate going back the other way, our rate of reaction for our N2O4 is real fast at first, as it's the only reaction that's going on at the beginning here, over on this part here. But as we continue on, some of that NO2 goes back to make N2O4. So our rate of the reverse reaction starts to kind of climb until they meet each other. So at that point, we can't distinguish the difference between the forward and the backward reactions. Their rates are the same. So beforehand, my rate of my N2O4, my forward reaction, is faster, right? And they meet together and equal each other at this point. And again, this is how we define the equilibrium. All right, now before we hit an equilibrium, we can still have reactions proceeding, all right? And we can have one direction, like the forward or the reverse, start to win out. So on the left side over here, we have a graph of concentration versus time, like we saw on the previous slide. But we are looking at reactants predominantly going towards the products. This is the reaction that's winning out. Okay, sometimes you'll see these harpoons kind of shown bigger or smaller to kind of give the idea of which reaction is kind of winning out. And then if they're the same size, it's equilibrium. That's not a technical thing. It's just kind of more of a little teaching thing you'll see. So, like on the previous slide, we start with a bunch of reactants in blue and not so much products in orange. And as the reaction goes on, we lose reactants, we get products. And so over time, our rate is increasing for our products to kind of reach the rate of the reactants direction. The forward and the reverse are kind of getting to the same place. So at this green line here, our rate of our forward direction of the reaction is greater than the rate of the reverse reaction. All right. Once we hit this point here, around 4 seconds, where our rate of the forward reaction is equal to the rate of the reverse, our reaction is at equilibrium. And then we can see we're at equilibrium because our concentrations are no longer changing. Now, over here, we reach the same kind of equilibrium. Our concentrations stop changing, and my line is actually probably a little bit early there. It should be over on the 4 seconds. I'll have to change that in my slides. But our purple line, our equilibrium, should be about the same spot, about the same concentrations, but kind of flip the other direction. So our products, in this case, go and start falling. We started with way more of this turning into this. So at the beginning, at this green line, our rate of our forward reaction is less than the rate of our reverse reaction. So overall, we have a net reverse reaction happening until we hit that equilibrium. So predominantly, we're going from products to reactions, We're driving the reaction in this direction until we hit that equilibrium point. Okay, when our concentrations level out, when our rate going in the forward direction is equal to the rate going in the reverse direction. All right, so graphing out things is great and all, but sometimes we don't have data over the course of a reaction. We only have it, at the beginning or in the middle or at the end, where we may have it at equilibrium, we might not. So we can mathematically determine when a reaction is at equilibrium by using the concentration values of a reaction that we have, or by using the partial pressures of the gases involved. All right. The value that we calculate using those concentrations or partial pressures is called the equilibrium constant, and it is a big K. We also have something called the reaction quotient, right, which is going to be calculated the same way. Its symbol is Q, big old Q. Okay, basically it's the same sort of math setup, but it equals K at equilibrium. Q is essentially our equilibrium constant when we're not at equilibrium. We haven't hit that point yet. And later on, we'll talk about how it tells us what the reaction is doing, kind of like the demonstration before with a reaction that is working towards hitting equilibrium. Okay, so let's say we have this reaction still, this N2O4 going in a reversible reaction to make two NO2s, but also simultaneously two NO2s meeting up to make N2O4. Okay, so if we have equilibrium when the rate of the forward direction equals the rate of the reverse reaction, let's look at what the rates would look like. So I don't have data for this, but we can write out a rate law. Okay, the rate law for any reaction is typically a little rate constant K, and then we have the concentrations of whatever reactants are involved. So for the forward direction, let's do this in blue. In the forward direction, we have N2O4 becoming NO2. So this is our only reactant. So this is going to be the only thing with a concentration involved here. We also have an order of the reaction up here, this little n. For our reverse reaction, do this in orange, we have our two NO2s going to make our N2O4. So that's the only reactant in the reverse case. If you were to flip this around the other way, this would be a reactant. All right. It also has a reaction order, this little M up here. If we were dealing with a reaction mechanism, this is usually where we'd have to look at the data and see how the reaction rate changes, figure out if it's zero order, first order, second order, or something weird, something like that. But we're only going to look at equilibrium for one-step reactions, elementary reactions. And the shortcut we had for that was whatever the coefficient is out front here is going to be the same as the reaction order. All right? So this is bimolecular. This has two essentially reactants. It's two the same molecule coming together. So we're going to have a 2 as our reaction order there. That's our exponent. And for N2O4, we have a 1 out in front. That's going to be our 1 here. Okay, so we can calculate the rate of the forward reaction or the rate of the reverse reaction as long as we have the concentration of the reactant for that direction. So for the reverse reaction, it looks like the product. Okay, so if these two have to be equal to each other, the rate of the forward and the reverse, then the rate laws I wrote out should also be equal to each other. So I can take my K forward times my N2O4 concentration and set it equal to my K reverse times my NO2 concentration to the second power. And that's where I get this right here. Use a different color. All right, now this is still kind of messy. I've just kind of put two things next to each other. So we're going to organize this a little bit. We're going to group the constants together, and we're going to group the concentrations together. Okay, so we divide our K reverse over to the left side. We divide this N2O4 concentration over to the right side. And what we get is this down here, where we have two constants over each other, and on the right side we have some stuff with concentrations of different chemicals. Okay, so we end up with this over here, this set of constants equal to this stuff with concentrations. Well, a constant over a constant is just a constant. This is a number divided by a number. So why do we need to keep these as k over k if we can just call it one new single number that's not going to change either? So if we take the rate constants, the forward and the reverse, and divide it, we should get some other constant. We're going to call it big K. We're putting together two little k's and we get a big K. I also have little EQ down here for equilibrium. So this is the big old K for equilibrium. This big old K, EQ, is called the equilibrium constant. And we plug in concentrations, or we can use partial pressures, to calculate what this K value is, this big old K. So we're kind of abandon the rate constants of kinetics. We're not going to use them directly. Just know that this is kind of the idea of where this is coming from. Okay, so our Kc is just the equilibrium constant when we use concentrations and plug those in. Kp is when we plug in partial pressures of the gases involved. Since we are using an example with gases in it, then we could do it in terms of concentration or we could do it in terms of pressure. Either way. The setup for this is called an equilibrium constant expression. It's basically just the math equation for our equilibrium constant. Okay, so we can calculate what this constant will be at equilibrium if we know the concentration of NO2 or the concentration or the partial pressure of NO2 and the concentration of N2O4 or the partial pressure of N2O4 at equilibrium. Okay, these numbers are not going to be equal to each other. Okay, they're not interchangeable, but we can convert them from one to the other if you really need to know. That part, the conversion part from Kc to Kp or back the other way, is not something AP requires of you. Okay, now we're not always going to have the concentrations or pressures at equilibrium. So does this stop working? No, the math setup is still the same. The only difference is we don't call it the equilibrium constant because we're not at equilibrium. Instead, we call it the reaction quotient. So if you just replace this with a big old Q for QC, this still works. It's just saying this isn't or may not be at equilibrium. Big old K means you are at equilibrium. The rates of the forward and the reverse reactions are equal to each other. We don't see any more changes in the concentrations or the pressures. Okay, so when we have equilibrium, the numbers you plug in for Q are going to be the same as you'd plug in for K because it's the same thing. We've reached equilibrium. So our Q is going to be equal to K at equilibrium. Okay, we want this to be useful for any reaction that we use, so just sticking with the N2O4 and NO2 reaction isn't really going to help us. So here's a general layout that I've written out and how AP writes it out, and this is the more official one. So if we have a reaction that is A plus B going to C plus D, where our little guys here, our little A, B, C, and D, are the coefficients of the reaction. Our equilibrium constant, or you could say our Q, not at equilibrium or at any situation like that, is going to be equal to these concentrations. Concentration of C, we use molarity for these. The concentration of D, okay, in molarity, and they're raised to the power of their coefficients, just like we did for the kinetic stuff. So C is raised to the power of whatever the little c is here, and D is raised to the power of the little d there, and so on. Okay, and then you've got your A and your B down on the bottom. Now, just trying to keep that straight all the time is kind of annoying. I don't like just having this random example of a fake equation hanging around with you and being like, okay, well, the C and the D has to be on top, and so which one's the C? And there's no D in this one, and it doesn't always match up right. So I like to think of it a little bit easier. The top, your C and D here, is basically your products. Your products go on top. Your A and B are your reactants, so they go on bottom. Okay, and again, this is reactants and products, just reading from left to right. Okay, if we were to read in this direction, these would be your reactants, A and B, and C and D would be your products. Okay, so when we've done stuff with delta, where we do like final minus initial, you can kind of think of this as final over initial. Our products over reactants instead of products minus reactants. Okay, so our products go on top, our reactants go on bottom. Then we have, again, whatever our coefficient in the reaction equation is, that goes up on top. So in this case, I've got M for my products and N for my reactants. Okay, so those are exponents there. All right, again, we call it big K if those concentrations or partial pressures are taking place at equilibrium, or we call it Q if it's just any time. All right, we can use concentrations for aqueous stuff dissolved in water, or for gases, and we can also do partial pressure stuff for gases specifically. Okay, now, since we're kind of basing this off of kinetics, we had some rules about what we can put into a rate law that are going to carry on over here. So when we did rate laws, we couldn't use solids or pure liquids. We also can't do that here. If something is a solid, right, that would be like a little s in parentheses in the reaction equation, or a liquid like this, then we don't include it. All right, that doesn't mean we like put something in there for it. It's basically a one. It acts like it's not even there. We ignore it when we put it in, just like we would do with the rate law. Okay, so if we have like an acid-base reaction, like H plus OH minus, making H2O. All right, then my Kc would have nothing on top. This H2O is a pure liquid. Okay, so I would just have 1 over. And then my reactants on bottom would be my concentration of my H plus to the power of 1 times my concentration of my OH minus to the power of 1. That would be my K or my Q. Kind of small there. Okay, so we only look for stuff that is gaseous or aqueous. And it's okay if we're missing something, if we just have a 1 on top or on bottom. There are cases where we only have aqueous stuff in the products and nothing showing up in the reactants that goes into the equilibrium constant expression. That is okay. Do not freak out if there are products or reactants that don't show up at all and we just have nothing on that kind of top or bottom side. Just put a 1 there if there's nothing. Time for some technicalities. Now, when we plug in a concentration or a partial pressure, like over here or over here, we are not plugging in the units with it. If you go further in chemistry, we call this like a chemical potential or chemical activity. That doesn't have units. It's a little odd. It's like standardized. So when we plug in a molarity, the big M unit does not go with it, which is great because otherwise having strange numbers, as your reaction order or stuff on bottom not canceling would make your units wacky for your equilibrium constant, and it would make all the math that goes with it impossible. So thankfully, we just basically drop the units. Whatever our molar concentration is, we're using molarity, not molality or percent or something like that. or a pressure in atmospheres, not kPa or something like that, mmHg. We just plug in the numbers and then we drop the units and we just leave it at that. So anytime you calculate a Q or a K, that is going to come out as a unitless number. Now also, I'm going to put in a little disclaimer here. When I show you the kind of rate laws coming together to make the equation that looks like this and looks like this, it makes sense, and it is true that the rates of the reaction going, forward and reverse equal each other at equilibrium. It's not really the reason why we get this equation anymore. The math looks like it works, which is great, but okay. Now also, I mentioned before, if we are working with QC or QP or KC or KP, these numbers do not come out to be the same. These are both reaction quotients or equilibrium constants, respectively, but that doesn't mean they're going to come out to be the same number because we're plugging in different values here or here with concentrations or pressures. Okay, so there is a way you can convert a Kc to a Kp or vice versa using the number of moles of gas that are involved in a reaction, but that is not covered on the AP exam. So I wouldn't worry about it. Just if you want to scratch that itch in the back of your brain, yes, there is a way we can go from one to the other. No, you don't need it. You don't need to worry about it. Don't go commit this to memory or anything like that. Let's try some examples. Okay, so we have three reactions here, and they're all reversible, which means we can write out a K or a Q expression for all of these. Okay, so in all these cases, for any time we've got a reversible reaction, we can write a Q or a K, specifically in equilibrium. If we've got a reversible reaction, we've got products, we've got reactants, and the reactions go in both ways at the same time. So we've got, for A, two O3s changing into three O2s and then back the other way. If we wanted to write out the expression for this, our K is going to be equal to products over reactants. Okay, in this case, we've got gases on the left, we've got gases on the right. So nothing is stopping us. All our products and reactants are going in here. So my product, reading from left to right, is my O2. So it's going on top. We're being asked for KCs, not KPs. So I'm going to do this in terms of concentration. So I'm going to do brackets here. Molar concentration. This is going to be raised to the power of the coefficient, so it's going to be O2 to the third power, divided by my reactants, which is my O3, again concentration, and it's going to be put to the power of its coefficient 2. All right, so this is our Kc expression for this guy right here. All right, our second reaction also has only gases, but this is a little bit different as we have multiple reactants. That's okay. We just stick them next to each other and they multiply to each other, kind of like the A and B and the C and D in that past slide. So let's write this out. Kc is going to be equal to our products over our reactants. Our product is our NaCl. Its coefficient is a 2. So I'm going to do this NaCl to the power of 2. My reactants are NO. The NO has a coefficient of 2, so that's got a power of 2. All right. And my other reactant is my Cl2. All right. Now, Cl2 is the formula of the chemical itself. Its coefficient is a 1. So if you want, you could write the 1 up here, or you could just leave it out, kind of like what we would do in rate laws. Okay, so this Cl2, right, does not get like doubled because it's Cl2. We just look at the concentration of this dichlorine gas and we plug it in. All right, let's do this last one here. C. Ag plus 2NH3 gives us AgNH3 and then it goes back the other way. So again, we're going left to right, and there's still nothing tricky here. Aqueous, aqueous, aqueous. So everything's getting put in. So what do I put on top? Doing like Dora the Explorer. Point to the products. Let me get my mouse pointer back so it really fits. Up, up, click. Okay. I've got my concentration of Ag parentheses NH3 2 coefficient of 1, so to the first power over my Ag plus in brackets, and then times the concentration of my NH3. Its coefficient is 2, so it's to the power of 2. Okay, let's see if we got those right. Hey, that looks pretty good. I don't see any errors as far as I can remember. If you'd like to get some more practice for yourself, which I highly recommend, we've got these down here. The work isn't shown for them. We don't have the analyze and plan thing. I just stole these from the book, so you can always go back and find more. But we've got our A and B, our two other reactions here.